This is me, Kunal Murke, and today I am here with a new topic, which is deep learning. Introduction to deep learning. Deep learning is a powerful subset of machine learning focusing on algorithms inspired by structure of the human brain. It employs neural networks to process vast amount of data, enabling complex patterns recognition and decision-making capabilities. The rise of big data and increased computational power has significantly advanced deep learning techniques and their applications. The deep learning is transforming industries by providing solutions for challenging problems in the fields like healthcare, finance, and transportation. History of deep learning. The journey of deep learning began in 1950s with the development of first artificial neural network models. Significant progress was made in 1980s with the introduction of backpropagation algorithm for training multi-layer networks. In 2012, the success of AlexNet demonstrated the potential of deep learning in image classification, sparkling renewed interest in the field. The recent years have been seen breakthroughs in the natural language processing and other domains, expanding the deep learning's reach and impact. So, the neural networks basics is important to be learned, where neural networks consist of interconnected neurons organized into layers, which are input layer, hidden layer, and output layer, which processes the data and learns the patterns. Each neural receives the input, processes it using a wait and activation function, and passes the output to the next layer. Weights are adjusted during the training using optimization algorithms to minimize the difference between predicted and the actual outputs. Activation functions introduce nonlinearity, enabling the new network to learn complex relationships within the data. So there are different types of neural networks. There are feed-forward neural networks, convolutional neural networks, recurrent neural networks, generative adversarial networks. Feed-forward neural networks, the data flows in one direction from input to the output, commonly used in classification tasks and simple predictions. Convolution neural networks, which are also known as CNNs, are specialized for image data, employing convolutional layers to automatically detect features and reduce the dimensionality. Recurrent neural networks are designed for sequential data, which are capable of maintaining context and memory across the time steps in the input sequences. And generative adversarial networks comprise two networks, a generator and a discriminator, that complete, allowing for the generation of new data instances. So the training deep learning models is also very important task. Training deep learning models involves preparing large data sets, which should be diverse and well labeled for effective learning. The training process consists of forward propagation to calculate the predictions and backward propagations to update weights based on the errors. Regularization techniques help prevent overfitting, which ensures the model generalized well to unseen data while maintaining performance on the training data. Hyperparameter tuning is crucial for optimizing the model performance, involving adjustments to learning rates, batch sizes, and natural neural network architectures. And then comes activation functions. Activation functions introduce nonlinearity into the network, allowing it to learn complex patterns and relationships in the data. ReLU, which are also known as rectified linear unit. These are widely used due to its simplicity and effectiveness in promoting sparse activations while avoiding vanishing gradients. Sigmoidal functions are the outputs which are between 0 and 1. sustainable for binary classification tasks, but can suffer from vanishing gradient issues. Tan-H outputs between -1 and 1, providing better convergence than the sigmoid function, often used in the hidden layers of the networks. Then we also have loss functions. Loss functions quantify the difference between predicted and the actual values, guiding the optimization process during the model training. Mean square error, commonly used for regression tasks, measures average square difference between predictions and the true values. Cross-entry loss, a key loss function for classification problems, measures the performance of a model whose output is a probability. And selecting an appropriate loss function is crucial for model convergence and overall performance in the specific task. Deep learning has revolutionized numerous fields by enabling significant advancements in the tasks that require complex pattern recognition. Computer vision applications include facial recognition systems, image classification, and self-driving car technologies transforming how machines perceive the visuals. Natural language processing, which are used for language translation, chatbots, and sentiment analysis, enhancing the communication and understanding between the humans and the machines. Healthcare provides predictive analytics for the diagnosing diseases and analyzing medical images and personalizing treatment plans based on patient data. What are the challenges that are faced in the deep learning? Training deep learning models requires extensive labeled data, which can be costly and time consuming to obtain and curate. High computational requirements pose a barrier to the entry. Necessities access the powerful hardware and resources for effective training. The interoperability of deep learning models remains a challenge, often resulting in black box issues where understanding model decisions is difficult. Bias in training datasets can lead to biased models, highlighting the importance of ethical considerations in an AI development and deployment. So, what are the future trends in the deep learning? The emerging trends in the deep learning indicate a shift towards more efficient and interpretable models, driving the further advancements in the field. Transfer learning enables models trained on one task to be adapted for another, saving time and improving the performance on limited datasets. Reinforcement learning involves training agents to make decisions through the trial and error method, learning to the innovations in the robotics and automated systems. Explainable AI focuses on developing models that are interpretable, ensuring that AI systems are transparent and trustworthy in the decision making process. What is a case study? AlphaGo, a landmark project by DeepMind that showed deep learning's capabilities in complex strategic games like Go. The system used deep learning reinforcement, combining the neural networks and also the Monte Carlo tree search to evaluate the possible moves and the outcomes. AlphaGo's success against the World Championship highlighted the deep learning's potential in strategic reasoning and complex problem solving scenarios. The achievements of AlphaGo have inspired ongoing research in AI, influencing advancements across the various domains beyond the gaming. So, what's the conclusion? Deep learning continues to evolve, driving innovation across multiple sectors by providing solutions to a complex problems. The ongoing developments of new techniques and architectures in enhancing the capabilities of deep learning models. Ethical considerations such as fairness, transparency must be prioritized as artificial intelligence technologies become more integrated into the society. The future of deep learning promises exciting advancements that could reshape the industries, improve efficiencies, and enrich the human experiences. So, at last, I would like to thank all of you, and I hope that you have gained valuable insights regarding this topic.